Hi, so this is going to be one of the most descriptive video there is. Okay, so in this video we are going to study the entire architecture of CNNs. These are certain layers that we have in the CNN architecture and we will study about all of them. The first thing that we'll start with is filters. Okay, so before we get into the theoretical explanation, I just want you to have an analogy. Now imagine you are having an stencil. Okay, if you know what stencils are, the painters when they paint and they have to paint a logo of a certain company, then they don't actually paint it. They have something like this. Okay, they have something like this of metal, and what they do they just keep it on the surface that they want to paint on, and they spray paints. Okay, and when they remove this stencil, the logo is printed on the surface where they want to print. So keep this analogy in mind. Okay, now let's start with the filters. Now suppose we have an image, okay, and we are having a diagonal edge in the image. Okay, and what we want to do with filters is we want to detect if our image is having a diagonal edge or not. So suppose we are having 3 by 3 image. The image is of 3 by 3 pixels. So this is the image. This is the pre-processed version of the image. Okay, we have a diagonal here, okay. All right, so what we do, we have this other matrix, and we actually keep this matrix. Just try to visualize, we just lift this matrix up, and in this matrix, in this pre-processed version, we keep this matrix at every possible sets of data. Okay, so we will put it where red is, we will put it where pink is, where blue is, and where brown is, and the 4 possible different parts of the A matrix pre-processed version will be multiplied by B. And what will be the result of this? When we multiply, suppose we are multiplying the first red part. Okay, this part, if we are multiplying with B, the result is going to be something like this. Okay, so the part which we had highlighted in this other matrix will increase, and the part which we had not highlighted, which we had made as 0, will become 0. Okay, so this is the purpose of this other matrix, and this matrix is what we call as a filter. Okay, so and what this particular filter does, it is a diagonal edge detector. Okay, so suppose we are having a this filter and the values are this. Okay, so what it does is it scans the entire image. Okay, suppose we have thousands of rows and columns in our image matrix, then what it does, it is kept on all the possible parts of our image, and wherever it identifies that I can get some type of diagonal, it enhances that particular value, and wherever it identifies that there is no diagonal, then it suppresses that value as 0. Okay, so what is basically happening here is that this filter is actually scanning the entire image. This filter is actually scanning the entire image. If I take example of this again, so this and this is my hand, so this is scanning the entire hand, and it basically scans where it can get the enhanced values of a particular shape that it is trying to detect. So this is the concept of filter. So this is the diagonal edge detector. Now these filters can be used to detect diagonal lines, vertical lines, and colors. Okay, so this was for the diagonal lines. For vertical lines, we could have something like this, right? Or for colors, we can have very high intensity of matrix, and it should be multiplied with the color of a certain type. Okay, so or we can have a different value for different colors, and we can use that. Now the filters identify features. We can have filters that detect specific color or specific shape. Basically we can have user defined filters, and we can proceed as our application demands. So this was the first concept, filters. I'm telling this concept, this one video is going to be very detailed. Okay, so it may also increase the size, by the way, the time limit. The next thing that we have to study is convolution. What is convolution? Okay, in the previous step, in the previous concept, we saw we had a 3x3 matrix and we had a filter. This is the F1. Okay, and this is a diagonal line detector, by the way. And the output that we get from this filter, this one filter, is what we call as a feature map. Now this feature map, what will this feature map contain? This feature map will contain the position of the diagonal lines in our image. It will completely scan our image for all the diagonal lines there can be, and the processed version, the processed output, the feature map is going to have all the positions of the diagonal lines that our image is having. Okay, so yeah, if you remember in the last video when we were discussing about the CNN, we had discussed the architecture, and we said that they work in progression. So the first layer will detect lines and circles. This is how it is detecting lines and circle. It uses the filters. Okay, so now suppose for the same image we are also detecting lines, we are also detecting a lot of things. We are detecting colors, shapes, and we are having 16 filters. Basically we are detecting 16 different things. So we will have 16 different feature maps. Okay, for every filter we will have some feature map na. So if I have a feature filter 1, then I will get feature map 1. Then if I have feature 2, I have feature map 2. So this process goes on. For every filter we have a different feature map. The process of obtaining this feature map while passing through the filter is what we call as convolution. So what is convolution? Convolution is like a forward pass. Okay, like we had forward pass when we were discussing about neural networks, right? ANNs, dense neural networks. Similarly, in the CNNs, convolution is similar to the forward pass. So the process of obtaining feature map while passing through the filter is what we call as convolution, and we can have different filters to identify different shapes and colors. That is very clear. Okay, now how do you decide the values of filter matrix? Okay, who decides these values, that a diagonal matrix should be 1 1 0 0? Who decides that? Like in ANN, these are basically like weights and biases in ANN. Okay, so like in ANN, in iteration 1 we randomly assign the values to these filters, then we train them using back propagation. This is the entire same concept. Okay, so in ANNs we were actually updating biases and weights. In CNNs we are updating filters. So the thing is that filters are not actually hard coded, they are not predefined. They are based on the type of developer, and they are based on the type of application. Okay, for color image, what we can do? For color image, to detect the colors, the color image will have structure something like this. It will be having a 3D structure where we will have R, G and B as in different places, and the filter will look something like this. This is how the filter will look, 2 by 2, but for each color we will have a different filter. And but after we process this filter, after convolution, the feature map is going to look like this only. 2 into 2. Okay, the feature map is going to have this dimension only, no matter if it is a colored or not. Okay, so if we are having 16 such filters, we will have 16 such feature maps. Okay, so 2 concepts down. The third concept we have to study is stride and padding. Now suppose take stride as alternations. Let me explain. Now suppose we are having a 5 by 5 image, as you can see, and we are having this filter of 3 by 3. So how you can scan through this filter this entire image? You will have filters in these positions. Now you will take parts of the image. First you will place it in the red place, then pink place, then blue place. Okay, so this is how it will scan. The process of generating feature map from different part of input is called as convolution. The stride, actually this is not right, this is not like iteration. So what is a stride? On first stride we will have feature map for every part. Okay, in second stride we will skip one part. So what will happen, in stride 2 we will look for red and then we will look for blue. So basically we are skipping one part. Okay, so this is what the stride is. If somebody is saying it is the first stride, that means you are taking every part into consideration. If it is a second stride, then you are skipping one part, then you are taking the other part in the consideration. The third stride, it means you are skipping two parts, and so on and so forth. So this is what the stride is. Another thing is padding. Padding is nothing but you basically pre-populate your boundaries of the image with zeros. Okay, so the padding we had used here is 1. Okay, if we create another layer, then it will be a padding of 2, right? So basically we are increasing the pixels in some way, but actually we do it for convolution. Okay, so that we are able to extract feature from the boundaries as well. Okay, from the boundaries as well we are able to extract the features. That is why we use padding. We are adding an additional layer of zeros to our input. Okay, so there is one formula here. The formula is we have to identify the output size of our feature map. Basically when we are given input size, filter size, padding and stride, and this is the formula that we use. We have input size minus filter plus 2 into padding upon stride and plus 1. Okay, so this is the formula. I'm not sure if you have that in your curriculum or not, but yeah. So this is a sample question. I would recommend you. It's a very basic formula based question. I mean this is something that should not be asked anyway. So just have a note these values down and just try to apply this formula. You will get the answer. There is no big thing about it, but the one thing that is here is that this is the size of one feature map. Okay, if there are a number of feature map, then you have to multiply this entire output size with the number of filters that we are having. So suppose we have input size, we have filter size, we have stride and padding. Doing this, we had calculated that 128 is the output size. 128 is our output size. So the output of one feature map is going to be 128 into 128. But we have 64 filters, right? So for the 64 feature maps, we will have the output as 128 into 128 into 64. All right. So we are done with the third concept. The fourth concept we are having is pooling layers. Now there are two types of pooling: max pooling and average pooling. First thing, we will understand what is the concept, what is the point of doing the pooling. Pooling basically is used to decrease the size of our data, size of our image. So we have, if we are applying 2 by 2 type of filter, then we have 4 parts then that we can consider from a 3 by 3 matrix. In maximum pooling, what we do, we will consider this one part. Okay, 1 3 this data of 1391, right? We will consider this matrix. In maximum pooling, what we do, it is used to decrease the dimension, as I just said. So what we do, suppose we have to decrease the dimension from 3 by 3 to 2 by 2. Okay, so what we do in the first part, we take the maximum value, which is 9, and we ignore the rest. We just forget about the rest. Similarly, in the next we have 3 4 1 0. 4 is the maximum, we take 4. We have 9 1 4 6, we have 9 as maximum. Then we have 1 0 6 2, then we have 6 as maximum. So this is the result of the maximum pooling. We have reduced the size of our image for sure, and we had taken the maximum of all the cells in consideration. Okay, this was maximum pooling. In average pooling, what we do, we take the average of all the elements that we are having. Okay, so that is it. And maximum pooling is used in more practical applications. It is usually happens now when you have an image of too many features, when you have an image of so many features, 1000 into 1000 image, and you only need an image of 250 into 250. A lot of the features are not actually important, so you can just ignore most of the features. You won't even notice them, okay, unless you are a professional. So this is where we use max pooling. In pooling, the max pooling is used more commonly, and pooling is used to reduce the dimension of our input image while preserving the most relevant data of the window. Okay, so this is the window basically. So we are having 4 windows. So in this window we are preserving the most relevant data. Okay, now this is 2 points. What is same copulation? Same copulation is when the size of the output matrix is equal to the size of the input matrix. Okay, so copulation kya hota tha? Copulation was the process of generating the feature map from the input. Now if the size of the input is equal to the size of the output that is generated, then we call it as a same copulation. Next thing we have, what is same padding? Same padding is when we pad our output matrix in such a way that it becomes equal to the input size. So basically what has happened, we have the input was of 4 by 4, okay, but our output is of 2 by 2, but we pad it in such a way, okay, that it becomes a 4 by 4 matrix. So that is what we call as the same padding. All right, so these were 2 terms. Okay, then we have the final layer. We are done with all the concepts. We have understood all the little points in the architecture. Now we are going to combine all of them into one. All right, so let's talk about the final layer. Suppose we have a real-time image, a color image of 227 by 227 pixels. Okay, and we apply a copulation, and applying the copulation we have generated 64 feature maps. Okay, and each we are basically applying 64 filters. We are applying 64 filters, and the dimension of those filters is 5 into 5 into 3. Okay, if you remember, when we perform copulation for the color images, we have to have the 3D filter. So that is what we have done here. Okay, and the stride is this and padding is this. So if we calculate the output size come out to be the same thing. It's 227 only. 227 minus 5, what is the 5 size? Okay, plus 4, what is 4? 4 is actually 2 into padding, then divide by 1. So it is an example of same copulation, by the way. All right, so this is the output that is generated. Now this output the output looks something like this. We have 227 into 227 into 64, the number of feature maps that we will be having. Now we remove linearity from the data. For that we apply ReLU. What ReLU does is it will keep only positive values. It will ignore the negative values. So in the data we will be having a lot of rows and columns. Some data will be negative, so it will ignore all the negative data, only the positive data will be transferred to the next layer, and the size is still the same. Then we apply pooling, and pooling is used to reduce the size. Okay, so when we apply the pooling of 2 into 2, basically the window size is 2 by 2. This is 2 by 2 window size. So the output of the next layer becomes of the size of the input. Basically the output after pooling becomes half of size. Okay, so this is the one layer, this is the one pass of CNN architecture. Let's talk a little bit about what are biases and activation we have used. Till now we have not actually considered any bias. Okay, we are just dealing with a lot of ideal situation right now. We have this input, right? We have this input, then we have this filter. Okay, in the filter we will have the weights. Okay, we have this filter, and in the filter we will have the weight, and the output that we calculate is actually given by this. Okay, input into weight plus bias. Okay, whatever bias we are having, and again the biases and weights are user defined, and similarly we calculate the output for all the cells. Okay, and then we perform ReLU, and only we keep the positive values. Okay, so this was about biases and activation, and now we are at the final thing. The final thing is to combine all the things that we have learned till now into one fully connected layer. So this is the fully connected layer, and this one iteration, this one pass is equal to what we did. This one pass is equal to this entire thing. Okay, this one pass I have also specified this. So this is this was the output. It has gone through this entire process. We are calling it convolution, ReLU, and pool. This is the entire process. Then we receive the feature map. Once again we go through this, we just keep on going through this process and updating our biases and weights and filters, and at the final layer, final extracted features are there. Okay, and these final extracted features are mapped to different neurons in the output layers. Now we want to know what we got out of our image. Okay, so if we have if we are having 1,000 classes, 1,000 classes are the categories now. So 1,000 class means our image can be cat, dog, a lot of things. Okay, 1,000 things our image can be. So we have to identify what is in the image out of those 1,000 classes. So for each class we will have a neuron here. So the output layer is also called as the Softmax layer, by the way. So this Softmax layer is going to have the dimension of number of classes into 1. Okay, and now, and this is basically what gives us the probability. This has become very similar to the ANN, by the way. So these entire these all neurons are going to give us the probability, and the sum of all the probability is going to be equal to 1. Okay, and it will give us the probability score in each category. So it will tell how much percent chances are of this image to be a cat, how much percent this is a dog. Okay, so this is the thing, and the number of neurons in Softmax layer is equal to number of classes. So here it is 1,000. So this was about the entire architecture of CNN. This was a very long video, and this was one of the most descriptive video, I think, of this section. And the next thing left in CNN architecture is regularization. That's it. Then we are done with CNN.